related to the question that was asked related to chemical characterization, this is of course an important aspect, because when working with geological materials, we do not only want to see structures, but also have chemical information. And for sure, those who are familiar with electron microscopy, this is the logic thing. But okay, the question is, what information can we obtain using X-ray CT? And if we go back to what Peter has talked about this morning about the Lambert-Beer or the Beer-Lambert law, this is also already providing you some answers related to what is possible with X-ray CT. It also links to the presentation of Jan. So what you detect in a detector, so the intensity that you detect in a detector is depending on the intensity that is coming out of your X-ray source, and then the interaction of your X-rays with your material. And your material there, the thickness of your material has an impact, so the S, but also mu. And mu is the linear attenuation coefficient of the object. And so this is linked to the chemical and structural composition of your material. And what you see there is mu is depending on the average atomic number of your material, the density, and also the energy at which you are scanning with. So, so it's always the combination of those three aspects. So if you go here to this graph, you can see for each element what the theoretical attenuation coefficient would be. And you immediately see that for elements which have a higher average atomic number, like lead, which is known, has a higher attenuation coefficient compared to those who have a lower atomic number. This also means that is also the reason why, for instance, lead is used to shield your scanners or protect yourself when working with X-rays if needed. But also the distance or the thickness of your lead will have an impact on if X-rays will penetrate or not, because it's the combination. But in reality, if you go here to rock material or sediments, on the left you have a sediment sample scanned with CT. On the right, it is a stone material. In reality, what you get is you see different gray values, which are linked to different attenuation coefficients. And you can clearly see what is in black is pore space. What is very bright, you know that this is something which is highly attenuating. So this could be something with a high average atomic number, but you do not know exactly what it is. And so if you have prior knowledge, of course, and if we go back to our sandstone, you know the material you're investigating, you can, if looking to a CT image, you can say, okay, this area is the air or the pore space. These grains are the quartz that I was expecting for my sandstone. And I know there are some highly attenuating minerals present like zircon. So probably this is zircon. But these are assumptions. You cannot say, I click on it and I know for sure this is zircon. Just working with standard X-ray CT. And so also when looking to those images, you could wonder, is this, for instance, clay present in my pore space? Because you see it's not completely black. It is something like in a gray value between pores black and the quartz, which is a bit more grayish. So you do not know, but if you have prior knowledge and you know your material well, you can already see a lot based on just standard CT. Another thing that you have to keep in mind is that we are working in a digital way, and so working with voxels and pixels and not in a continuous way. And an important aspect here is if you look to this Savoniere limestone, which was scanned, we know that chemically it's purely calcite. But you see that you have differences in gray values, going from very bright to rather darker. And this is something to keep in mind, is that when working in a digital world, the partial volume effect can play a role. Because when we reconstruct CT slices, we are looking at voxels, so volume elements, which it's similar like pixels, but then with a third dimension. So in X, Y, Z, we are looking at, for instance, if you scan it with a voxel size of 10 micrometer, that means that your voxels have 10 by 10 by 10 in dimension. And so what you see in a reconstructed slice in your volume is the average attenuation coefficient in that value, in that volume. And so this also means that depending on your voxel size, you will get a kind of averaged gray value of everything what is within your voxel. And here is an example, or where it is important, is if you have, for instance, your grain presented here as tissue 1, and you have your pore presented here as tissue 2. When you are reaching the physical border between those two, what you see in your resulting voxel is a kind of average gray value, which gives a mixture of the amount of tissue or your tissue 1 in function and tissue 2. So the more you have your tissue 1 present, or the more you have your grain, for instance, it will be a little bit darker. The lesser the content of tissue 1, it will be a bit brighter. So this is also challenging, because in reality, you want to, when going back to the talk of Ben, you want to segment it and have a good representation of your borders of your grains, for instance. And that is why resolution is a very important thing, what was mentioned and explained clearly by Jan Alterman. And the way to do so is typically, we try to work typically with small samples when using X-ray CT, because then we can work at the highest magnification, putting them as close as possible to our X-ray source, and therefore working at very small voxel sizes. So this is one way to solve this. So partial volume effect is a problem. On the other hand, it also can be of help. If you're only working with two materials, meaning, for instance, calcite versus pores, you can use the difference in gray value to get a kind of estimation of the total volume percentage of your pore within your voxel. So this is presented here. Assume that on the left, this is a voxel fully filled with air, a pore. Then you will have a certain gray value. On the right, you see a voxel fully filled with material, could be the calcite, very bright. And everything in between is a kind of giving information about the percentage of pores or the pore volume. You don't know anything about size, you just can get a kind of estimation saying, if you look to the reconstructed slice on the bottom, you can say, okay, in the middle, the very bright ones, this is pure calcite. On the right here, we have voxels filled with 80% of calcite and 20% of pores, and here probably it will be 40% of pores. So it can help you to say something of information below the resolution. But you have to keep in mind, of course, that also tiny elements present in your reconstructed slice can have an impact on your resulting data. And in geological material, often this is also the case, that you have small particles of iron, for instance, present, and they can influence also your average gray value. And also here again, therefore, the resolution is very important, because you want to limit this effect as much as you can. And I want to illustrate this with these two rough drawings. Just on the top, you see a sample which is just two materials, pores and gray material, and on the right you see how it could look when it is reconstructed with CT. On the bottom you see completely different composition, but having a mixture of different components, but the resulting image is also similar. And this is something to keep in mind when working with CT. So what can we measure? So I already said that the attenuation coefficient is strongly depending on the average atomic number, the mass density, and also the energy that we are scanning with. And if you look on this graph on the left, this is something you can calculate for whatever material you want to investigate with CT. So I refer also to the NIST database to do so. And what you see here is that if you know, for instance, that your material will be composed of calcite, gypsum, quartz, zircon, and magnetite, I don't know, it's just an example, you will immediately see, okay, how will the theoretical attenuation look like in function of energy? And what you see, for instance, is if you scan assume you are scanning at a low energy, then you will see, okay, the zircon has the highest attenuation, so it will be brighter. Then you will see magnetite, which has a lower gray value, lower attenuation, and then you go down calcite, gypsum, and the quartz. So based on this theoretical attenuation coefficient, you can already have a kind of estimate, okay, the brighter ones are probably this, or the less bright ones are probably another material. Important here to mention is that, of course, you immediately see that if you go to higher energies, it is like assume here at 300 kilo electron volt, you see that you cannot distinguish between the zircon and the magnetite just based on the theoretical attenuation coefficient. And also, so this is important to know. So this is also why acquisition is very important. This is why you try to find an optimal acquisition setting working at the right energy to see the questions that you want to solve. And so sometimes, so you would say, okay, then always scan at the lowest energy, because the higher your energy is, the lower your attenuation coefficient will be. Yes, but sometimes you have to find something in between, because if you're working with geological materials and they are very dense materials with a lot of heavy elements like ores, you need to also be able to penetrate the material, and you can only do so by going to a certain height in energy. So sometimes you are obliged to go for high energy scans, because just to get the information out. Again, there the sample size will be important, because if you can reduce the sample size, you will be able to go for maybe a little bit of lower energy to still get information coming out. So it's always trying to find the balance and the right acquisition parameters to then do all the other steps. So because of that, this is why with CT often contrast agents are used, because they typically have a higher linear attenuation coefficient, and so you clearly see them. And more information about this will be given later by Lawrence. But to give you an idea, if you go for cesium chloride, for instance, you can immediately see it is highly attenuating compared to all the other materials. And this is also why you see with CT these very bright areas, which is clearly the cesium chloride. And so if you are working with contrast agents, or you are investigating your samples with CT, I would suggest to also make this graph to get familiar in what you will be able to see even before scanning. You will be able to know, can I distinguish two materials from each other or not? And if you go back to this graph of the cesium chloride, where I also put some values for calcite, quartz, and gypsum, it brings us to one of the methods to try to reveal the chemical composition. And this was already done this is one of the standard ways or procedures that was done based on this theory, and this is called dual energy imaging. And so if you look to the theoretical linear attenuation in function of energy, you immediately see that if you scan your sample on an average photon energy, which is in the situation A, so very low, compared to an average photon energy which is higher, then you see that there is a shift in the way the attenuation coefficients are changing because of a KH jump. And so you see that if you scan at situation A, the cesium chloride has a high linear attenuation coefficient, but then the highest will be the quartz. And then you will have the calcite, so with the lowest gray value. Well, if you look on situation B, you see that there, first it is the cesium chloride and then it is the calcite. So you have a shift by just changing the energy at which you were scanning. And this can be used and is already also used, for instance, to get some estimations of the chemical composition based on this dual energy. So it is used, but still, if you keep in mind also the aspect of partial volume effect, it's not so easy, and there are a lot of aspects coming together. So another way is, of course, combining what we are very familiar with is with electron microscopy and all the information that is obtained there, because most of us are working with geological materials, so we know that you have a combination of techniques to characterize your materials. And one way you could use is, for instance, with CT, and maybe this is something important to mention, maybe not highlighted this morning. The benefit of CT is that you can just put your sample in it and you do not need to do any kind of sample preparation in principle. But if you do so, and if you polish your sample, for instance, like what is shown here, you can combine different techniques, like, for instance, first doing a CT scan of your block, then coating it, then put it in a scanning electron microscope, combining the chemical information and the mapping that you got from your surface or different surfaces, and then try to match the gray values that you obtained with X-rays combined with the mapping that you obtained with the chemical information of using electron microscopy. So this is a way people are trying to validate and get information. Of course, what they do is they only work from the surface information, and you do not really have the real 3D information of your sample in the middle. But this is also referring to what is called correlative microscopy, where people then try to find features, for instance, automatically or manually, where they match. So on the left, it is can be a CT image. On the right, it is a CT image. And in the middle, it is probably a backscattered scanning electron microscopy image. You see the different features. You can match the data. And then we are opening an entire research domain related to correlative microscopy. And so this is the way people are working. And another example here is that, for instance, if you combine the power of what was taught yesterday of the electron microscopy, you are able to get all the information. You can get the mineral classification, and then you try to match this with your CT data and try to get a kind of mineral phase segmentation, even in a kind of 3D way, but with some assumptions and knowing your material well. So another way of using CT could be combining micro-CT with XRF, X-ray fluorescence. And X-ray fluorescence, for those who do not know this, is also a technique to provide you the chemical information, similar like what you get with scanning electron microscopy possibilities. And so you also use an X-ray source. The X-ray from this source ejects electrons when interacting with the material. This creates then a vacancy. This vacancy is filled with an electron from the outer shell, and characteristics X-rays are emitted. And this information gives you chemical information. So what we did in the past, for instance, here we had a rock, and even on the macroscopical figure, you can see that it has that you can distinguish features. If you scan this with CT, you get different gray values, which you know these are particles with different chemical and density differences, but you do not know which one. If you then put this in a micro XRF system, you can get the superficial mapping and get the chemical information, similar like what you do with SEMIDX. And then you can, with some cluster analysis, you can try to identify the minerals, combine this then with the CT data and do some estimations. Similarly, so this was done for a few samples. We did some, on the left you see the CT scan, on the right you see the mapping of the different elements, and then you can have a kind of chemical information, and then we try to even we always linked the gray values with the chemical information from XRF and then have a kind of estimate. This made us build a first system, a Heracles system, which is also accessible via the transnational access, where you can have those two methodologies combined in one system, because going from one system towards the other is always a bit tricky. So here we have a scanner where we combine XRF and CT in one system. And the way it works is you have an X-ray CT setup. So you have a source detector, and in the middle you have your sample. And then we have two end stations, one for XRF tomography and one for confocal XRF. And so what you typically do is you scan the sample, and then after reconstructing, you can say, okay, I want to have a point analysis at this spot or at this spot, and then the system automatically goes to that XRF end station, and this way you can have the spectrum. And by doing so, you can draw lines on your surface, similar like what you do when you do a line profile with electron microscopy, get the chemical information of your surface. But if you want to go for 3D information, it is challenging, because XRF typically gives you information from your surface and also some information of your internal part. So here you see a limestone which was scanned with gold particles on top of it, and the gold is presented in green, but you only see information of the upper 200 micrometer, the chemical information, because the XRF signal does not comes out here. And so you only see a rather superficial information. But it gives you already a good combination between real chemical information and X-ray CT data. But as we are missing this internal part, we are also looking for other methods. And this comes to what Peter was talking about, that you have also different kind of detectors. And if you use, instead of a normal X-ray CT detector, a spectral detector or a hyperspectral detector, you can register other information. So if you look here, if you see here the setup, you also have a source, you have your sample, but you use another detector, which then you can get chemical information. And this is referred in literature to hyperspectral X-ray micro-CT or color X-ray CT. And I will show you what we are working currently on this. So this is not something which is normally regularly used, but there is a development ongoing related to this. And so you can buy hyperspectral detectors, and you have detectors sensitive for low energies and detectors sensitive for high energies. And then we just replace our normal detector with this hyperspectral detector. And then you can do you can combine and see what the differences are. And to illustrate this, here we have a pack of materials, of grains of quartz, tungsten, gold, and lead. And if you would scan this with normal CT, you would be able to distinguish, the quartz, and you see very bright grains, but it's impossible just based on CT and even with your prior knowledge to distinguish between the gold and the lead and the tungsten. So if you scan this same sample with spectral CT, you get this kind of reconstructed image, where you see that it is not so sharp as the one on the left, but this contains also the spectral information. And if you then are focusing on the grains you're interested in, you are able to distinguish between the gold particles, the tungsten particles and the lead particles. So this is a way to combine potentially just normal CT and chemical information, but this is still under development. And to conclude, I want to, yesterday there was a talk about, dynamic imaging and clay behavior. And so I wanted to give you this information that if you're interested in very high resolution imaging, but you cannot work with the FIPSAM, as was explained yesterday, which is destructive, of course, and you need 3D information in a non-destructive way, and you need also chemical information, and you also want to condition the sample conditions, so temperature, relative humidity. Tachographic tomography or also nanotomography is a possibility. This is not possible in one of the facilities that is offering transnational access, but this is possible at a synchrotron. And I just think it is important for those who are working in this field to know that besides using CT and electron microscopy, there are other ways of analyzing your sample. And typically what we do is we try to combine as much as we can in lab, and where we are limited, go to the synchrotron. And so here, as said by Peter, you have a parallel beam, and there the idea is you also use X-rays, but then from the synchrotron. You have your sample in the middle, and you are detecting diffraction patterns. You rotate this, and this is only also for small samples. But if you do this and you work with very tiny samples, here you see the setup of this, you are able to reach resolutions in the order of 45 nanometers, and even at the moment they go even higher. And so you have this information in 3D of your tiny sample, of course, but the benefit is that you can quantify, for instance, if you're working with clays, but you can also measure expansion of clay materials, because you can control relative humidity and temperature, or freeze your samples. You can do many things there. And combined with this, you can also get chemical information. So for instance, we could determine the liquid that was present inside our sample, which was on the bottom of our sample, which was in this case the glue that was used to glue our sample on our sample holder. So you can get also the chemical information. And this brings me to the end of my talk. So with X-ray CT, yes, you can get some information, but then you normally need prior knowledge, and you have to be critical. There are some ways to analyze your data using dual energy. This could help you, but it depends. And otherwise, ways to combine this is using X-ray CT for your structural information, and then combining this with other techniques such as the electron microscopy or XRF or other techniques that you are familiar with. People are working on really getting the chemical information, for instance, using spectral CT, but this is currently under development. It will be also something for the future, which I think is very realistic, but it will also, like each technique, has certain limitations. And there are also advanced imaging techniques when not working in the lab, but going to the synchrotron. But this is, of course, another way of trying to get access than to do your experiments, but I'm happy to help or provide you with information related to this. And with this, I would like to end and thank you for your attention. And I want to thank also the past and current members of my team at UGCT who are, were some of the things that I showed was, of course, the work provided by them.